Alright, 6. Let's get cruising with science class. Let me go some think the internet's working. Raise your hand quietly and we'll try to get our poor students at home to know that we're there. Okay, guys, yesterday we talked about our skill for the 5th time. What was the skill we talked about yesterday? Compare and contrast. Compare tells how things are alike. Contrast tells how they're different. And we watched that really neat, interesting video that used liquid nitrogen. We use liquid nitrogen to freeze things, guys. So we tried to drop temperatures, increase the pressure, and eventually made the water bottle explode. We put it inside a tin can. The tin can acted like a certainly.
It acted like a cannon.
It was a cannon, so we want to take all the effort instead of exploding it that way. It fired it up there. That hit the green pail, sent the green pail flying in the air. Super cool to do those things. The water that we had in there, guys, was what we're going to talk about today. It was increasing the amount of thermal energy that was available. So we're going to start lesson 1 today. We're going to learn what thermal energy is and how it's transferred. Let's get started on page 1. I need 4 readers to take out thermal energy so that we can learn what it is, so that I can then learn how it is transferred. Brooklyn, give us paragraph number 1. Kennedy, paragraph number 2. Kaylee, paragraph number 3. Nyla, paragraph number 4. Potential.
The total kinetic and potential energy of the particles in a substance is thermal energy. The amount of thermal energy depends on the amount of the substance. If you have a cup of water and you pour half of it into a part that is left has half the number of particles, it therefore has half the thermal energy that the full cup of water has.
Thermal energy determines how warm a substance is. One cup of water has more thermal energy than a cool cup of water. The warm and cool water have about the same number of particles, but the particles in the warm water are moving faster. They have more kinetic energy, therefore they have more thermal energy and feel warmer.
Okay, guys, we talked about thermal energy last chapter because it was on your test, although they didn't give you the definition of it until this chapter. But we did talk about kinetic energy last chapter. Kinetic energy is the energy you have because you're in paragraph 2. Find it. Kinetic means energy because of
Motion.
because of motion. Potential is energy you have because of position. So the best way I was taught this was, guys, a roller coaster. Here's my roller coaster. Okay, get on my little roller coaster. This is me scared out of my mind. We're going up this hill right here. When I get to the top of the hill, am I moving fast or slow? Slow. I have very little kinetic energy because my motion is slow. But I'm way at the top of the hill. My position has the ability to give me a lot of energy. So my kinetic energy is very low. My potential energy is very high. I go over this hill. What happens to my speed?
It goes fast.
I'm going way faster. My kinetic energy is going way up. My potential energy is going way down because I don't have gravity anymore when I get down here. So this would be super high kinetic energy, super low potential energy. Now I'm going to start going up this hill. What's happening to my kinetic energy?
It's going down.
It's going down because I'm slowing down. But what am I gaining? I'm gaining potential energy. Okay, true or false? This first hill on a roller coaster will be the same height as the second hill. True or false? This one will be taller than this one. Or this one will be shorter than this one. When it has to be true of the second hill, taller, smaller, or same?
Has to be taller.
Has to be smaller. Somebody tell me why can I not get back up to the same height? The next one is going to stop and go down like this. If kinetic's going down, then potential should be going up. If potential's going down, then kinetic should be going up. Did I lose energy anywhere else?
No.
Yes. Where? What am I losing energy to?
That hill.
Good. Definitely losing it to the hill, but why can't I get to the same height? Cam.
Because you can go back down. You can go back down.
Partly true. Angle would just be how fast I lose it though.
Because gravity pulls it down.
One, gravity's pulling on me. What else causes me to lose energy, guys? I think you gotta go back 2 chapters. We're in machines. Machines produce that ruin your energy. Armani, friction. So you'll never get back to the same height, guys, because there's friction here as you ride these rails. And so you won't be quite as tall as you go through that. How do we get you on a roller coaster up this first hill?
The level that you're on.
Okay, one, I could start you up here, right? Some roller coasters you climb to the top and you start up here. Most of the time you start down here because we don't want to make you climb all those stairs. And then we get you up this hill by, there's a machine that does it, guys. Usually it's a chain underneath. You know, we roll there, also you hear this, and you're like, doomsday is, I hate roller coasters, but some of you are like, yeah, this is so exciting. Okay, but we have to use mechanical machine energy to get you up here. Then, guys, in most roller coasters, we have one machine, and after that, we just let you go, and gravity does all the work. Okay, there's a few things we want to go through. Number one, we didn't do anything out of paragraph 1. We looked at the liquid glass picture. But number 1 says from paragraph 2, all matter is made of particles that are always moving. Number 2, it's energy due to motion. Number 3, potential energy is energy due to
Position.
Then you got your 3 states of matter. Number 4, particles in a gas move
Freely.
but they don't pull strongly on each other, guys. So I can spread out however I want. I can move freely in a gas. Number 5, in a liquid, we can only flow. We used the word slide when we did it way back in the day. We said spread out, slide. And then in number 6, in a solid, they can only vibrate. That they can't move from their fixed position. Somebody tell me what the word fixed means in science class. When I'm in a fixed position.
Still.
Still, I can't move. Remember we had a fixed pulley? Boom, put it somewhere, don't move it. We had a fixed pulley. Number 7, you have your definition. Put all the kinetic and potential energy together and you have thermal energy. 8 is what's really important, guys. The amount of thermal energy depends on the I have a glass of water and I have a bathtub of water. Which has more thermal energy? The bathtub. The more water I have, the more thermal energy I have. Okay, so I'll ask you those questions on your test. What's going to have more thermal energy? Full glass or half glass? Full glass. Whatever gives you more. That goes right along, though, with not number 9. Thermal energy determines how
Warm.
Warm a substance. And then number 10, guys. A warm cup of water has more thermal energy than a
Cool.
cool cup of water. So the hotter you are, the faster the particles move. That gives you thermal energy. So on your test, what has more thermal energy? A half a cup or a full cup?
Full.
10 degrees or 50 degrees?
50.
50 or 100?
100.
Ooh, tough one now. 50 degrees of a half a cup or 40 degrees of a bathtub? Why do you say 50 degrees with a cup?
It may be less water, but
We have temperature, so we're factoring temperature.
40 degrees of a bath
Why did you say 40 degrees with the bathtub?
because it's more water.
Because there's way more water. So I didn't give you enough directions. Most of us would say the bathtub. If I said, I have a full, huge bathtub, you go, well, that's a ton of water compared to a cup. That'll make up the less temperature. So, guys, the more you have of something, the more thermal energy you have that goes along with it.
So like, okay, so using like your example, so if you have like a 40 degree of the bathtub, and then isn't that going to equal up to your body temperature?
You just led us into the next page perfectly. What's going to happen to the temperature of the bath water? Is it going to get to my 98.6 or not? Let's find out. I'm super excited.
I'm sorry, I didn't try to do
No, that's just perfect. I'm just, woo! Here we go. Guys, we're going to talk about heat. Follow along with me. We'll play fill in the blank. You've probably measured your kinetic energy many times, but you may not have known it. Temperature is a measure of your average energy of an object's particles. When you take your temperature with a
Thermometer.
your body heat increases the kinetic energy of particles of the liquid inside that thermometer. The thermometer then shows the average kinetic energy of the particles in your
Body.
temperature is not the same as thermal energy. Temperature depends only on the average kinetic energy. Thermal energy is the... Oh, I'm in the math class now? What does sum mean?
the whole altogether.
Addition.
Yeah, add it all together. So thermal energy is adding all of your kinetic and potential energy together. That's not temperature, guys. Temperature is just your kinetic energy. Unlike, hint, hint, look at us to compare and contrast from yesterday, right? Unlike thermal energy, temperature does not depend on the amount of a substance. If you split an object in half, each part has half as many particles, but the temperature does not change. The average kinetic energy is the same. Okay, so we're back to our bathtub and our glass analogy. I have a glass of water at 50, I have a bathtub at 50. Which one has more thermal? The bathtub. Because it's a bathtub. Which one has a higher temperature? Cup at 50 or bathtub at 50? Which has a higher temperature?
Oh, no.
They're the same. They're both at 50. In temperature, guys, we don't care how much you have. In thermal energy, do we care how much you have? Yes. So on the first page, when we're talking thermal energy, amount matters. On the second page, when we're talking about temperature, amount doesn't matter. Okay? Third paragraph. Thermal energy can move from one substance to another is called
Heat.
heat. Always moves from a
Warm.
to a.
Cool.
An increase in temperature means that heat moves from a substance. When heat moves into a substance, the average kinetic energy of the particle rises. The extra kinetic energy increases the particle's
Vibration.
vibrations. Particles vibrate faster when a substance is heated. The movement of heat from one substance to another can occur between objects that touch the objects and objects that don't even touch. There are three types of heat transfer. They are known as conduction, convection, and
Radiation.
let's see how you did on your notes. Number 11 is where I left off. What is the measure of the average kinetic energy? Temperature. It is not the same as
Thermal.
because temperature only depends on the average
Amount.
kinetic So as I go on with number 12, guys, it only averaged kinetic.
Okay.
Thermal as not only kinetic, it's also potential. Temperature, just kinetic. Thermal, kinetic and potential, we have to put them together. Number 13, also a difference. Temperature does not depend on
About
the amount. I don't care if you have a bathtub or a cup, if it's 50 degrees, it's 50 degrees. Definition number 2 for today, 3 for today, whatever we're up for today. 14, thermal energy can move from one substance to another, that's called
heat.
heat always goes from warm substance to
Cooler.
this is gonna challenge you guys. On the next page we'll talk about it. I put ice cubes in my drink to make it cold. True or false?
True.
That's how we talk, isn't it? I can't make something cold. That would be putting cold into it. I can't put cold into it. I can only take heat out of it because it always moves from hot to cold. If you say put ice cubes in there so that you're making it cold, that would say you're moving from cold into the hot beverage. We're taking the heat out of the hot beverage. We'll talk about that on the next page. 16. When heat moves into a substance, the energy of the particles
Rise.
goes up. So the hotter it is, guys, it has more thermal energy. That's why we make those statements. Number 17, there's 3 types. You had to fill in the word conduction, and we'll talk about conduction right now, and then tomorrow we'll get the other 2 of convection and radiation. Let's take out conduction. Because I'm getting really rattled up, I couldn't put cold in, and what in the world is my crazy teacher talking about? Let's figure it out. I need 3 paragraphs on the conduction page. I'm super jacked. Armani, you got paragraph number 1. Ryan, you got paragraph number 2. Kaylee, paragraph number 3.
The temperature of the ice cubes is lower than the temperature of the lemonade. The particles that make up the lemonade are evaporating faster than the particles of the ice. When the ice touches the lemonade, the particles in the lemonade bump against the ice particles. This causes the ice particles to move faster and faster. Heat flows from the warmer lemonade to the cooler ice. The lemonade particles slow down. Conduction of heat has warmed ice and cooled the lemonade.
When heat moves by conduction, the particles in the substance do not change their location. Energy is passed from particle to particle as the particles vibrate and bump against other particles. This movement of energy may occur between a warmer substance and a cooler one. It may also occur between the warm particle of an object and the cooler particle of the same object.
Okay, let's go through it, guys. Number 1, you got conduction. For conduction to transfer heat, the objects must touch. So when you think conduction, think they need to be touching. That's what we did with number 18. Heat transfer between 2 objects that touch is called conduction. Which way did they go? 19. Heat always flows from warm into the cooler. So in this case, they were in paragraph 2. We were talking about lemonade. How does ice really make my drink cold? It doesn't put cold in, it takes heat out. So the ice is saying, let me absorb this heat from the lemonade. So if my lemonade was at 80 degrees and I drop in my ice at 30 degrees, we're going to start pulling the heat out, and the ice is going to melt, but it's going to pull the 80 down to, let's say, 50 degrees. I now have this nice cold drink, don't I? Okay? It's not because we pushed 30-degree temperature in. So guys, there's nothing wrong with saying ice makes my drink cold. But in science class, on your test, you just have to know that we always go from hot to cold. So if I ask you, how does it make it cold? It pulls the heat out. So I have a refrigerator at my house. It's supposed to make things cold. It does that by absorbing heat. It's taking the heat out. So I got done eating my hot dish yesterday, put it in a Tupperware, stuck it in there, boom. We're starting to pull that out, blast it through its engine in my refrigerator and shove it out into the outside air. Okay, number 20, conduction of heat has warmed the, and by warming the ice, you naturally cool the lemonade because we're absorbing it. 21, when heat moves by conduction, the particles in the substance do not actually change their.
Location.
22, energy is passed from particle to particle as the particles and
Vibrate.
then bump against each other. 23, this movement of energy may occur between a
Warmer.
and a cooler one. So that's your lemonade, guys. I have warmer lemonade, it's bumping into the ice is absorbing that heat and making it cooler. 24 says it may also occur from a warm part of an object to the cooler part of the.
Same.
So I took my metal spoon and I'm cooking supper, right? And I set the metal spoon on the pan. What's gonna start to happen to that metal spoon? It's gonna start to, well, if I leave it there long enough, we're gonna start to feel the heat now. Where's it hotter? On the handle that I'm holding or the spoon part that's on the pan? The spoon part, that's heat. So it's just saying, hey, this is hotter, it's colder, and we're gonna start moving from the heat into your hand, Bauer, and eventually you're gonna get yourself burned. Now, metal is a good conductor, guys, so that's gonna go really, really fast. That's why lots of times when we cook, we use wooden spoons, because wood doesn't conduct heat that much, and I'm not gonna get myself burned using it. Q.
Is that the reason, let's talk about the ice cubes and the water. Is that the reason why when you put it in the water, it cracks?
Yes. Well, it cracks because what we're really doing is we're changing the size of the ice. So the ice is trying to warm up. When it warms up, it wants to get bigger, and so it's going to crack. Now, water's the exact opposite. When water hits it, it wants to shrink. Well, it can't, so it crushes itself. Okay.
So you know, like the ice in the big